Thank you very much. And let me first thank the organizer for giving me the opportunity to give these talks online. I wish I could be there. So I'm going to tell you about recent work that I hope will shed some light on, will provide an alternative way to look at the Fermi liquid, a bosonized approach to Fermi liquid. So the plan of my talk is first to review Landau's Fermi liquid theory, and then describe a feature of the Landau Fermi liquid theory that it can be viewed as a theory that describes the dynamics of the shape of the Fermi surface. And then we are going to talk about the mathematical framework that allows us to parameterize these shapes, called the methods of coadjoint orbits. I'm going to try to explain how this theory of Landau Fermi liquid can be viewed as a motion on a coadjoint orbit of the group of canonical transformation. And then from this method of coadjoint orbit, we are going to be able to reformulate Landau Fermi liquid theory as a field theory. My collaborators in this paper that was published, that was put on the arXiv in March, was Luca Delacrétaz, postdoc in Chicago, Yi-Hsien and Umang Mehta, who are students at also at the University of Chicago. So in 1956, Landau proposed a theory of Fermi liquid. His vision, his insight is that even when the original fermions, which could be, for example, electrons in metal, interact strongly with each other, the low energy degrees of freedom, which are quasi-particles near the Fermi surface, due to the restriction in the phase space, cannot decay very quickly into other quasi-particles, so that when we are at low energies, we have a gas of long-lived quasi-particles. Landau's theory of Fermi liquid can be applied to various situations in nature. For example, in helium-3, electrons in metal, neutrons in neutron stars, and presumably other situation as well. Sometimes one hear a description, a simplified description of Landau's Fermi liquid theory as a free theory of Landau quasi-particles, a theory of free quasi-particles. However, as I will show you, the structure of Landau's theory is very different from the free field theories that we usually learn in textbooks, like free scalar field theory or free Dirac field theory. To see that, it is instructive to first describe, review the structure of Landau Fermi liquid theory in the way that Landau originally described. Landau described a Fermi liquid in terms of the phase space distribution function. So this function f as a function of t, x, and p satisfied the Liouville's equations, or collisionless Boltzmann equation, or Blasov equation. This equation basically describes, one can view it as a description of a swarm of points in phase space. So these points in phase space move both in x and in p, and the velocity of, so here is the equation for free particles, free fermions. The velocity of motion in the x direction is the derivative of the energy with respect to p, the group velocity, and the velocity of motion in the p direction in phase space is the force that acts on the particle. And here is the Liouville's equation that describes the evolution of this collection of particles. So it looks like a classical equation. On the other hand, the quantum nature of the Fermi liquid enters in the possible values of this function f. This f can be, due to Pauli's exclusion principle, can be only between 0 and 1. And moreover, if we start our evolution of the system from an initial condition in which the distribution function is either 0 or 1, so we have a Fermi surface, and inside the Fermi surface f equal to 1, and outside the Fermi surface f equal to 0, and then under the influence of any external electromagnetic field, f will always remain either 0 or 1. And that is because Liouville's equation preserves phase space volume. And so if we follow the trajectory of a single particle, at that place, f is always, the value of f never change. So it will be either 0 or 1. So Liouville's equation can be viewed as an equation that describes the time evolution of the shape of the Fermi surface. We start at t equal in minus infinity in the ground states. If the system is rotationally invariant and two-dimensional, then the ground state has just a circular Fermi surface. And then we turn on the electromagnetic field, and the system will deform in such a way that the Fermi surface is always sharp. The surface that separates f equal 1 region from f equal 0 region is always a one-dimensional line. But the shape of that line, of that Fermi surface, can change both in time and in space. So these dynamics of shape describe both the evolution of the shape in space and in time. If we have the Liouville's equation, we can use it to compute any physical response functions. For example, if we want to know the linear response of the system to an external scalar potential, A0, we need to solve the Liouville's equation, the linearized version of Liouville's equation, where the electric field is the gradient of this A0. So linearizing the equation and solving it, we find the two-point functions for the density, and this formula written here coincides with the result one would obtain from a much more quantum method of computing one loop diagram, one loop fermionic one loop diagram in perturbation theory. In the regime where the velocity, when the momentum is small compared to the Fermi momentum. Nonlinear response can also be obtained by solving the Liouville's equation beyond the linear approximation. And the validity of the result that we obtain in this way is the regime of validity is small omega and small q, q much smaller than the Fermi velocity, Fermi momentum, and omega much less than the Fermi energy. Landau also told us how to modify this theory to take into account the interaction. The new parameters that one needs to introduce in the theory is called the Landau parameter. It parameterizes the energy of a quasi-particle at point x and p. It parameterizes how it depends on how this energy depends on the deviation of the distribution function at other values of the momentum, but at the same point x. So this Landau parameter is a function of two momenta, and in fact, it's only a function of the angle between the two momenta if the system is rotationally invariant. The kinetic equation that one write down has minimal modification, basically all due to the fact that the energy of this quasi-particle include a new term that depends on delta F, and one has to take that into account when we write down the velocity of this particle in P and in X. In X, and along the p-axis. Landau Fermi liquid theory is a very successful phenomenological approach to the low energy physics of fermionic system. On the other hand, it has a feature that it is not a field theory. It is formulated in terms of the equation of motion, a kinetic equation, not like a field theory in textbook where we start with the Lagrangian of the action. And so one loses the access to a large toolbox of effective field theory. We don't have the insights from the Wilsonian approach to field theory. We cannot compute, for example, systematically the corrections to Landau Fermi liquid theory within the framework of effective field theory. So it would be nice to reformulate Landau's Fermi liquid theory as a quantum field theory. And another benefit that one may hope to get from this reformulation is that one can hope to approach the problem of non-Fermi liquids, which one example of such a non-Fermi liquid is 2+1 dimensional fermions at finite density coupled to a U1 gauge field. And this situation presumably can be realized in the physics of the half-field Landau level, where the fermions are the composite fermion, and the composite fermion coupled to each other by changing the photon of an immersion gauge field. There have been previous approaches aiming at the reformulation of Fermi liquid theory as an effective field theory, and these approaches, broadly speaking, can be divided in two categories. In one set of approaches is approach based on fermionic effective field theory. We try to write down an effective action in terms of the fermionic quasi-particles. So this has started with Benfato, Galavotti, developed further by Shankar, Purchinsky, and others. The second set of approaches can be called Bosonization. And Bosonization is a very elegant approach in 1+1 dimension. One can map precisely a fermion to bosons and vice versa in 1+1 dimension. But this approach is very clumsy in higher dimensions. Specialists who have worked with this bosonized theory in higher dimension recognize issues under the name of patches or curvature, etc. So we would like to find a simpler bosonized theory. Within this talk, I want to solve one concrete problem, answer one concrete question, which is, can one formulate Landau Fermi liquid theory as a field theory with some action S as a function of some field phi, so that the variation of that S with respect to phi give us the Landau kinetic equation? And it turned out that the answer to this question is yes, one can do that using the method based on the mathematical notion of Coadjoint orbit. The main idea of this approach is the following. If we look at the distribution function, we can act on this distribution function canonical transformation that acts in the phase space of a single particle phase space and deform it to another shape. And any state with a sharp Fermi surface satisfying the condition that the number of particles in this state is the same as in this state can be obtained from this reference state by acting a canonical transformation on it. That's the main idea. So let's talk first about canonical transformations. Infinitesimal canonical transformation can be parameterized by a function in phase space x and p, where x goes to x prime, given by x minus epsilon gradient of f over p, and p goes to p prime plus epsilon gradient of f over x. So these equations basically are the describe time evolution of a single particle under the influence of a Hamiltonian f given by function f. Classical Hamiltonian, this particle satisfied the move under a Hamiltonian given by f in a infinitesimal times equal to epsilon. We know that Hamiltonian evolution preserves Poisson bracket, so this transformation is a canonical transformation. We can take two of these canonical transformation and then act them one after the other with different orders and compute the commutator of the two canonical transformations, and one find that the commutator of two canonical transformation is again a canonical transformation given by a function which is the Poisson bracket of the two functions that parameterizes the two canonical transformation for which we compute the commutator. So the infinitesimal canonical transformation form a Lie algebra, and by exponentiating this canonical transformation, we get the Lie group, which is a group of finite canonical transformation, which can be visualized as time evolution under unit time, not infinitesimal time, but a unit time following a given Hamiltonian f. So e to the f is element of the Lie group of canonical transformations. Now, another notion that I want to introduce, which one may find this introduction of this notion a bit pedantic, but is very useful, is the notion of the dual space. That is a space, the space of all function f of x and p, so that for a function for an elements in the dual space and the elements of the Lie algebra f, both given by function in phase space, we can compute the scalar product by integrating the product of small f times big F over the phase space. And there is a physical interpretation of this scalar product. If we think of the element of the Lie algebra, big F as an observable, so for example, this big F may be p squared over 2m. Then this observable is the kinetic energy. Then we can think about small f as something that gives us, that parameterizes a state. It's a distribution function of our many-body system, and the scalar product between small f and big F is then the average of the observable big F in the state f, small f. So this make the this formula is basically a classical analog of the quantum mechanical trace of the product of the density matrix and the operator. Instead of a quantum mechanical trace, here we have just the integral over the phase space. Now we can define the adjoint and co-adjoint group actions that acts on the Lie algebra and in the dual space. So if we have elements of the Lie group that I call here U, which is the exponents of some G of some element of the Lie algebra, we can define the action of U on F this way. Basically, it's a adjoint representation. This is how an adjoint representation of this group U is defined. We take the commutator and then exponentiate it, and then that would be the adjoint representation. And we can define the so-called anti-adjoint representation, or sorry, the co-adjoint representation. In this way, in our particular case, the formula is exactly the same. The action of group elements on small f is given exactly by the same formula when we write it in terms of Poisson brackets. And one can check that these group actions preserve the scalar product. If we have small f and big F, when we rotate it using the same element u, the result would have the same scalar product as the original small f and a big F. Okay, so now let us think about the following object. Let us take a reference state. State here means a vector in the dual space. In this case, this reference state is chosen to have the distribution function given by the distribution function of the ground state of a rotationally invariant Fermi liquid with momentum Pf. So the distribution function is 1 inside the Fermi sphere with radius Pf and 0 outside. Now let us define the coadjoint orbits as a collection of states that can be obtained from this F0 by canonical transformation. So we take this state F0 and then act on that all possible canonical transformation. So then we will find, what we find is our state with a sharp Fermi surface, because canonical transformation is basically just a Hamiltonian evolution with some Hamiltonian, which preserve the sharpness of the Fermi surface. So we have still have state with sharp Fermi surface with the same total number of particles. So we have the coadjoint orbit is defined as as state with a sharp Fermi surface, and therefore our Fermi liquid lives in that space, in the sense that if we start our evolution with F0, then the Fermi liquid will always remains on the coadjoint orbit. Therefore, our task is now to parameterize the coadjoint orbit and to write an action that describes the Landau's time evolution on this coadjoint orbit. So the coadjoint orbit can be thought of as a coset in the following way. So we said that, so now I'm going to use notation that I'm familiar with from the theory of the unitary Lie group, but it can be made precise in this case as well. If U is an element of our group G of canonical transformation, then we can rotate F0 to a new F equal U F U minus 1. But by doing so, we have a certain, if we want to parameterize the point on the coadjoint orbit using U, we have ambiguity. That is because there exists an invariant subgroup that we call H that preserve F0. F0 go to F0 under the action of any element V of that group. And so if we have a U, that would be equivalent to UV. U and UV transform F0 to the same F. And thus, this way one can see that the coadjoint orbit, which is the space of all these F, is a coset G over H. So let's work in perturbation theory around the reference state F0. So we act on this F0 group element U that is slightly different from 1. So it's exponents of minus phi, where we think about phi as some small function, and expands all the equation in linear order in phi. So for example, the new distribution function obtained from F0 by acting exponents of phi minus phi on it will be given by a theta function of, but now the theta functions describe a Fermi surface that is deformed in space. Instead of Pf minus P, here Pf changes, and this change depends on this phi. And there is an ambiguity, as we said, and this ambiguity turn out that this ambiguity U equivalent to UV, where V is or is any canonical transformation that leave F0 invariant, allows us to fix the gauge. Instead of thinking of phi as a function of X and P, we can require that phi does not depend on the absolute value of P, but depends on the angle parameter of the momentum. So phi is only a function of X and theta. roughly speaking, it's work like this. First of all, we have to find out the subgroup of all the transformation that leave F0 invariant. And doing the algebra, it turned out that e to the power of alpha leave F0 invariance if this function alpha vanishes on the Fermi surface. And then the equivalence group is the equivalence in linear approximation is the equivalent between two functions which differ from each other by a function which vanishes on the Fermi surface. Now we can choose this function alpha to be the f phi of x minus p minus phi on the Fermi surface, but at the same angle theta. This alpha clearly satisfies this condition, and so this alpha belongs to the invariant subgroup. And using this alpha, we can transform phi to a new function, which is now does not depend on the radial coordinate, on the absolute value of p, but only on the angle theta. So the coadjoint orbit is parameterized by a function phi, which is the function of x and theta, which now we can interpret that as bosons. We have a description of our Fermi surface in terms of infinite number of bosons, one boson per each point on the Fermi surface. Now, the action that one can write down consists of two parts. The action has the Hamiltonian part, which is more trivial than the the part with one time derivative. So this part is basically this is an explicit form of the part of the action with time derivative. U is the element of the Lie group that correspond to the point F on the Fermi surface. So this S has to be a functional of the point on the coadjoint orbit, and here U is the group elements that rotate F0 to F. Now, if one look at that, one might see a certain problem because, as we said, there is an ambiguity in defining U. One point on the coadjoint orbit may correspond to different U. But it turns out that one can show that replacing U by an equivalent U changes this Lagrangian only by a total time derivative, and so the action would change only by the boundary term. Another way to see that is to rewrite the first term in an alternative form as an integral, as a Wilsonian action. We have to introduce a new coordinate S, and this part of the action can be written as the integral over of the so-called Kirillov-Kostant-Souriau symplectic 2 form, which I will define in the next transparency. And so in this way of writing the action, the Lagrangian is completely invariant under this gauge equivalence, but with we do that with the expense of introducing a new dimension, like in the Wilsonian formalism. The actions, the Hamiltonian is simply the energy of our fermionic system in the state with a given distribution function F. So, for example, for free fermion, that would be just the scalar product of F with the kinetic energy, which can be written also in the alternative form by using the invariance of the scalar product under action of the group. Okay, so this Kirillov-Kostant-Souriau symplectic 2 form is one of the notion well known in mathematics, and the formal definition of that 2 form is the following: if you take a point F on the coadjoint orbit and draw two tension vector, delta F1, delta F2, then this delta F1 and delta F2 can be put into correspondence with two elements of the Lie algebra, capital F1 and capital F2, and this two form is defined as just the scalar products of F with the Poisson bracket, with the commutator between F1 and F2. And mathematicians managed to prove a theorem that this omega does not depend on the choice of the Lie algebra elements F1 and F2. There is also a certain ambiguity in defining F1 and F2. And furthermore, this form omega, this two form is closed. And so this closed two form allow us to define a Hamiltonian evolution on the Coadjoint orbit, given the Hamiltonian. Okay, so the action, to summarize, the action has two parts. The first part, with first derivative, is a Berry phase term. Basically, it can be thought of as the Berry phase that a Fermi surface acquired. Our system acquired when the Fermi surface is deformed. The shape of the Fermi surface is deformed. And the second part is just the Hamiltonian. Landau's Fermi liquid theory just tells us that this Berry phase term is universal. That is, it does not depend on the interaction between the original fermions. The Berry phase acquired by a change of shape of the Fermi surface is the same for all Fermi liquids. Now let us explore this action to the quadratic order. So we know that we work around the ground state F0, parameterize the points on the Coadjoint orbit by function phi, and expanding the action to quadratic order in phi, we see the action has the form of integral over d theta of the collection of action of chiral boson, one chiral boson for each theta. So n of theta is the unit vector with component cosine theta and sine theta. So gradient, n times gradient basically is the gradient along the direction of the momentum. So the density operator is an integral over the density of all these chiral bosons, each point theta. And using this quadratic action, we can compute the two-point function of the density. So in the fermionic theory, what we have to do is to compute the one loop graph. But in our bosonic description, what we compute is just a tree graph, which is propagator of phi running between two row vertices. And one can check that the result is exactly the same as in the quantum theory of a fermion. We can also go to nonlinear order because all these terms in the action can be expanded further in power of phi. We have cubic order in phi term as well. So for free fermions, the cubic order in phi depends on not only on the Fermi velocity, but also on how the Fermi velocity changes with momentum. But what is more interesting is the Wessel-Minowitten term. When we expand it, we see that there are coupling between within this chiral boson at different value of theta. So we have d theta here. So boson at different theta start to couple to each other in cubic order. And so we can use this Lagrangian to compute three-point function of the density. If we take this one loop diagram. So in the fermionic theory, the three-point function of the density is given by a one loop diagram. Actually, by two one loop diagram where the fermion runs in clockwise and counterclockwise direction. In the bosonic language, we have a collection of just three diagrams, one containing the cubic interaction between the boson, and another diagram due to the fact that the density contains part that is quadratic over phi. And so in the fermionic language, it turned out that there is a cancellation, there is a subtle cancellation between two of this fermion loop diagram with fermion running in the opposite direction in the regime when omega is of order q, and both are small. Each of these diagrams behaves like 1 over q in the small q limit, but there are some the leading 1 over q single behavior cancelled, and the sum is of order q to the 0 power. In the bosonic language, it turned out that each of these diagrams are is already of order q to the 0, and so so the bosonic theory is better in some sense. It's better in the way that it manifests the cancellation between two fermionic diagrams. We don't have to compute this diagram to see that they are q to the 0 power. Furthermore, we can check that we have checked that this very complicated dependence on the external momentum and frequency in this graph is reproduced in the bosonic theory. One can also include the Landau parameters in the theory by modifying the Hamiltonian. So the Hamiltonian now is not the Hamiltonian of a free particle, but contains also interaction, this Landau parameter interaction between delta F. And one can even go to higher order in derivative and higher order in delta F, like in effective field theory. Now we have we can extend the theory in several directions. Before extending, we make the following remark, that if psi is a fermionic operator, then the 5 fermionic bilinears defined this way form a closed algebra. And in the long wavelength limit, this closed algebra is actually the algebra of canonical transformation. So that allows us to extend the formalism to spinful Fermi surface. All we need to do is to extend the algebra of canonical transformation to include the operator psi-Decker sigma A psi, where sigma A's are the Pauli matrices. We can also extend our theory to the BCS theory, to the case when the BCS order parameter is present. We need to extend the algebra to include psi-Decker operator and psi operator. Together with psi-Decker psi, these operators form a closed algebra, though this algebra is larger than the original algebra of canonical transformation. But we can still apply the Coadjoint orbit method with a new algebra, with a new group. Okay, to conclude, the method of Coadjoint orbits provides a natural way to write down an effective field theory of a Fermi liquid. It leads to a nonlinear bosonization. That is, it leads to a boson, a rewriting of fermionic theory in terms of bosons. A free fermion theory becomes a interacting bosonic theory. It reproduces linear and nonlinear Fermi liquid response, and some very non-trivial cancellations in the Feynman diagram for nonlinear Fermi liquid response becomes explicit in the bosonic theory. And we hope that this might be a suitable starting point for the study of various phenomena beyond the Landau's Fermi liquid theory, for example, non-Fermi liquid. Thank you very much.
Yeah, thank you very much, Professor Son. That was very insightful. So I was wondering about your Berry phase term. So if I think in the quasi-particle picture, the Berry phase is obtained from parallel transport in K-space around the Fermi surface. But is it possible to relate your Berry phase term to that Berry phase in momentum space?
Berry phase in momentum space. I think I'm not completely sure, because it's here. The situation is that it's not a single particle state that we are talking about. It's a many body fermionic state with fermion filling a a Fermi sphere. And so we have to somehow compute this Berry phase of a mini particle state. And I don't know how to compute it, but I suspect that it has to reproduce this formula. Or at least for free fermion, it has to reproduce this formula somehow. But I haven't done this calculation.
But I guess maybe my question is, can you apply this formula to, say, the Fermi surface of a wild fermion?
Of a wild fermion. If the Fermi surface is finite, that is, if the chemical potential doesn't go right through the Dirac point, if it's above the Dirac point, then this formalism can be applied to Y fermion as well.
But where does the Berry phase, the momentum space Berry phase of a wild fermion, how does it enter the theory?
Yes, so here the Berry curvature of the Dirac fermion is 0. This Berry curvature is 0, and so in the classical de Wilms equation, we will not see the effects of this Berry curvature. I suspect that one has to the effect of the Berry phase of pi around the Fermi surface has to be seen somewhere, but it's not in this classical approximation that I'm working on here. So this is something that I have not and still have to think about.
Okay, thank you. We have 2 questions from the audience.
So, so in the Fermi liquid, there's a 0 sound in the fermionic picture, but in your bosonic picture, does that translate to, like, for example, like a Goldstone mode?
So each of these phi, so there is an infinite number of Goldstone in some sense, infinite number of phi, which has coordinate dependence, but also has theta dependence. And when we write down action for phi, let me show you this action. Here, if for free fermions, this action does not couple different theta with each other, but if we include Fermi liquid interaction, boson with different theta will mix with each other. So we have to diagonalize a matrix with off-diagonal matrix elements, and diagonalizing that matrix, we see the 0 sound, but also an infinite number of state in the particle hole continuum.
Thank you.
But as a follow-up question to that, a 0 sound, in your theory of 0 sound, it would still be linear bosonization. Am I right?
Yes, it's a linear. It can be seen in the Landau theory as the solution to linearized kinetic equation. And in our formalism, it would be a consequence of the quadratic action.
We have a second question from the audience.
Okay, so I also want to ask how this nonlinear bosonization, where it stands. So we know that in bosonization in a 1D system, the whole entire Hilbert space between the fermion and the bosons, they are kind of related, and any kind of excitations, like electron hole excitations, can be considered in both situations. Whereas it seems that in this nonlinear bosonization, the state that you have are like this functional f, this lower case f, which seems that to me that you don't really have the degrees of freedom of quantum mechanical excitations, like electron hole pair creation and so on. So then it looks more like a semi-classical dynamics. Is this correct?
I think this might be our intuition in this case is not doesn't, maybe we are misled by thinking about the this fermion loop diagram. For example, when you compute the 2-point function of current, think about that as coming from a particle hole pairs as the intermediate state in this diagram. But in this bosonic action, we managed to do that with just the infinite number of bosonic degree of freedom, because infinite because theta has a phi running inside here. And so somehow if this particle hole pair has low small total momentum, somehow that state should exhibit itself somehow equivalent, in some sense it's equivalent to a boson.
But here this is like a virtual process, and your state itself at the beginning and end, I guess it's still, you don't have this electron hole pair.
All the electron hole pairs are all the electron hole pairs with small total momentum are linear combinations of this phi. So this 3-point function is even more striking, that this seems to be a diagram with all kind of particle hole pairs running inside, contributing to 3-point function, but the result is exactly the same as computing the tree graph with boson. Yeah.
And okay, so and then you quantum mechanically calculate this using your bosonic theory. So in the bosonic theory, it's really a fully quantum mechanical and and not like you do semi-classical field theory with this. Is this correct?
Yeah. In this theory, we can look at the loop graph in phi. So construct a theory with the loop diagram in phi, and that would correspond to two diagrams that are more complicated than this diagram. Yeah.
Okay. Now I'm convinced that it's quantum mechanical. Yeah, thank you very much.
You may have time for one last question from the audience.
Yeah. So in this formulation, can you apply some kind of Wilsonian renormalization group to this approach?
Yeah, we have been trying to think of that's what we want to do. This approach should be quite convenient for Wilsonian renormalization group. We just need to know how Tx and theta rescale during renormalization group transformations. So we have made some. We just look at the problem, the old problem of fermion coupled to a gauge field, or fermion coupled to a scalar, the non-Fermi liquid, and it seems that some known result can be done with some. We can see that the non-Fermi liquid behavior arises because there are the interactions are relevant in the Wilsonian sense, for example, by power counting.
But in this case, then how do you separate fast mode and slow mode?
So we have modes in phi which are long wavelength, and mode of phi that are short wavelengths. So phi has index, phi is a function of x and theta. So we have modes that are fast in x and slow in x. So that's how we have fast, and these are all bosonic mode. There's no fermion anymore.
But what about theta? So, for example,
What about theta?
yeah, you can decompose that in terms of angular momentum, for example, right? Then this
I think
high
here
angular
it's
momentum-
actually we have only made some very preliminary investigation of that, but it looks like that thinking about theta not in terms of angular momentum but in terms of theta itself is more convenient.
I see.
We have modes that are that varies over. So we have to think about how theta rescale. So the problem with non-Fermi liquid arises when there are many particles moving in the same theta direction. But it's an interaction between modes with similar theta.
That's
That
right.
becomes
Right.
that becomes subtle and has become relevant. Yeah.
All right. Thank you.
Thank you.
Maybe as a follow-up question, in Schenker's renormalization group, there's a renormalize in energy towards the Fermi level. But it seems like if you're only able to renormalize in your method in real space, that's quite a different type of renormalization. Right?
I think our hope is that it is a more convenient way to do renormalization group, since we don't have to deal with different discrete patches on the Fermi surface, but we have to deal only with the continuous theta. So for example, we have this action where we don't have to think about how the different patches overlap with each other and what are the interaction between boson in different patches. Everything looks like just a continuous variable. And so that in this sense, technical sense, it seems more convenient than the usual way, the Shankar-Tunchinski way that one to do renormalization group.
Okay, yeah. Thank you, Professor Sound. This was very illuminating.
Thank you very much.
Yeah, so this is our morning break. Yeah, so I guess we'll return in about 20 minutes.